Howdy! In this example, we're gonna go over how to calculate the weld leg length. We're gonna be using geometry factors, and this is example 11.3. All right, let's take a look at a figure first. What do we have? We have this tubular member. It is 400 millimeters tall, and there's an arm attached to it. It's 400 millimeters long, and at the end of the arm, there's this force being applied of 1,500 newtons parallel to the x-axis, but pointing towards the negative x-axis. What we want to figure out is essentially what is the weld leg length? What's the size of the weld that needs to be over here to keep this guy in place? Now they tell us that all the parts of the assembly are made of ASTM 836 structural steel, and that they are welded with E60 electrode. Again, what we want to do is determine suitable leg length for the weld, and we're going to be assuming a safety factor of 2.5. Before we go ahead and solve it, first let's go over the general procedures, which is 1, propose the geometry of the joint. Number 2, identify the types of stresses that are acting on that joint. Number 3, analyze the joint and determine the magnitude and direction of the forces on the weld due to each type of load or type of stress from number 2. Next, we're going to calculate the resultant force. This is done by combining the forces vectorially at the point where we believe the forces to be maximum. And number 5, we're going to divide the force on the weld by the allowable force. This number is provided by the electrode material to determine the leg size, or H, over here. All right, let's get to it. Remember the general steps, and the first one is to propose the geometry of the joint or the weld. When we look at this guy, right, this guy is a tube that is going to be welded to a plate, with the tube being circular in cross section, right? Hopefully you can see that the best thing to do is to go ahead and weld all the way around that tube at the base of the tube. So the weld is going to look like a circle. That's step 1. Step 2 is to identify the types of stresses or forces that the weld is going to see. So the first one, or the most obvious I should say, here's what we're going to use like previous knowledge from combined loading to figure out what the reactions, or not the reaction, but what the forces would be right at this point where the weld is, right? So the first one is, hopefully you can see that the force of 1,500 newtons is gonna end up trying to shear the weld, right? And this force is acting towards the negative x-axis. What else can happen? We'll see. Well, this force is at an arm, right? So relative to the base, this force can kind of make the whole thing rotate about the z-axis, something that looks like this. So what that means to the weld is, depending on which points we're looking at, the force is going to be like in different directions, right? The shear force generated from this torque. So up in the front is going to go like this, on the side towards the back it looks like this, and on this other back side it looks like that. What else can happen? Well, the force is some distance above the plate, right? 400 millimeters above the plate. So the other type of loading that this welding can see is essentially a bending moment. Oops, sorry. Put my hand in there. About the y-axis, something that looks like this, right? What does it mean for the weld? Well, depending on, again, which point we're looking at is going to be subject to different stresses. The ones here at the front is going to try to tear this one up like this. In the bottom, right, there's going to be some compression. And then, yes, this is a bending moment. So anywhere along the neutral axis, this one over here, there's going to be no stresses. So before we go ahead and do more analysis, what we need to figure out is which of the points is the worst point for the weld. Okay, and when we look at the case for the shear, this is the shearing force. Don't think this of transverse shear, just a shear force that acts all the way on the weld. So really there's no good or bad plates, they're all seeing the same shear loading. For the twisting or for the torque, let me call it twisting. Well, it depends on which point we're looking at, right? But it's pretty much the same severity all the way around to that weld. Now, the different one is going to be the bending, right? We already know that there's some areas that sees no strays about the neutral axis. Then the material, the weld material in the back is under compression per se, and the one in the front is under tension. Here, I hope you can see that if I have this tube assembly and I kind of making it tilt back with that force, the weld material in the back is really not going to do much. And the reason is because as we push back, that tube wants to compress, right? But it's just running into that plate at the bottom. So the plate is helping support that tube, not so much the weld. Now, that's very different up in the front, right? Because as you're trying to put that load, is trying to twist it towards the back, the front part wants to lift, right? And what's gonna, the glue that keeps it stuck together to the plate is that weld, right? So it's gonna put it under tension. So that means that for the bending case, this point over here is the worst case. So once we figured out this is the worst case and all the other ones have the same, right? Automatically it means we have to analyze that point over there. Again, this last case was from the bending. So next, what we're gonna do is we actually calculate, we're gonna calculate the force per inch of weld depending on the different types of loading. Again, we got shear, which the formula is just V by AW. So the force due to shear is just the shear load divided by AW. The force due to twisting, if we look over here, is TC by JW, where T is just the torque, T is the distance from kind of the centroid of the weld to the weld, and then JW. And then the force due to bending is going to be the bending moment divided by this quantity SW. So those are the formulas. The next things that we would do is we would actually look at a book to look for geometry factors for these weld analysis. I went ahead and put the ones here for when we have a circular weld, right? A weld that goes all the way around. And it's telling us, for example, that this quantity AW is simply pi times diameter. We call it AW. You might think of it as an area, but remember when we're doing this weld analysis, we're thinking of the weld not as an area, but just as a line. So like in one dimension. So here we go. So let's go ahead and substitute the values. In this case, the shear load is 1,500 newtons and AW is just pi times diameter. In this case, the diameter for this problem, it says over here, is 40 millimeters, right? So this is going to be equals 40 times pi. And this is going to have units of millimeters, right? Because the diameter is in millimeters. Now that we have these values, we can go ahead and calculate already the force on that weld due to the shear, right? Which is 1,500 newtons divided by 40 pi millimeters. And this is going to be equal to, if I plug it in the calculator and don't make any mistakes on it, I'm getting 11.937 newtons per millimeter. And you're going to see that every time we're going to get these forces acting on the welds, they're going to have units of a force per millimeter. Okay, next one is the force due to twisting, right? So, oops, sorry. So let's go ahead and figure out. First is the torque. What is the torque acting on it? remember we're calculating the moment about the z-axis. So the force is 1,500 newtons, and the distance from that force is going to be this one here, is 400 millimeters, which brings the torque to 600,000 Newton millimeter. Next is this quantity C. Now it's not in this table, but the quantity C, it's always from the centroid. So in this case, like the centroid where that weld would balance would be right at the center. And so the centroid really is just the radius of the circle in this case. So the circle being a diameter of 40 millimeters, that means that C is just going to be 20 millimeters. Next quantity is JW. And we can barely see the formula over here. Let me show you right there. Oops, right here. And the formula is pi times d cube by 4. So we go ahead and figure out, put in the value. So it's pi times the diameter, which is 40 millimeters cube, right? This whole thing cube, divided by 4. If we plug that into the calculator, I get 50,265 millimeters cube. Right, so now we have T, we have C, and we have JW. We can go ahead and put it in that original equation. So the force due to twisting is the torque, 600,000 Newton millimeter, times C, which is 20 millimeters, divided by JW, which is 50,265 millimeters cube. If we plug this into the calculator, I get 238.7. And look at the units on top. We got newtons, we got millimeter times millimeter, so that's millimeters squared up on top, but we got millimeters cube down below. So 2 are gonna cancel, and we're gonna have units of newtons by millimeters. Next, let's do the last one. We need to figure out what the bending moment is. Remember, this is when this 1500 Newton force is making this assembly tip over the y-axis, right? So the moment is just going to be 1,500 newtons times 400 millimeters. This is from the height over here. Well, we calculated that already, right? It's the same one as the torque. So this is going to be 600,000 Newton millimeter. Next, we need this quantity SW, which we get it from this figure over here. And this one is saying that SW is just pi times the diameter squared divided by 4. So we got pi times 40 squared divided by 4. And we plug that in the calculator. I get basically 400 pi, and this is going to be in millimeters squared. So let's go ahead and put everything into the force equation, and we end up with a bending force of, in the top, the bending moment, 600,000 Newton millimeter, and the bottom is W, which is 400 pi millimeters squared. We type that in the calculator and we get the number 400 77.5. And look at the units. We got newtons up and top. And then we got 1 millimeter on top and millimeter square at the bottom. So one of those is going to get canceled. And we have Newton millimeter. We're almost done. We're in step 3. We calculated, we determined the magnitude and direction of the force on the weld due to each type of loading. Next one, which is step 4, we have to calculate the resultant by combining the forces vectorially at the point where they're maximum on the weld. So we already said that our weld is circular. Here's our X and our Y axis. And that this point over here, this is where the forces are maximum. We already said that we have a force here that is shearing, right, towards the negative X axis. Next, we have a twisting force, which is along the Y axis here. So we have a twisting force in this direction. So let me go ahead and label. This is Fs. This is from Ft. And then the bending one, which is this one way at the right hand, is trying to tear this up, right? So we have here in the Z direction, Fb. We need to combine these guys vectorially, so we just are gonna sum them, right? So that we can get the resultant. So the resultant is actually from here to there. Now this is not to scale, but that's a more or less representation of the resultant force. How are we gonna get it? Well, we have component in the X, a component along the Y, and a component along the Z. So we can calculate the magnitude of that resultant by just getting the square root of the sum of the components squared, right? So we have Fs, which is 11.937. We're gonna head and square it. Plus, along the Y, we have 238.7 squared. And then along the Z, we have 477.5 squared. Whoops. And this is going to give us our resultant. So we type this in the calculator. I end up getting 533.9. So I'm just going to say 534 millimeters. Now this 534, I'm sorry, not millimeters. Bummer. This is Newton per millimeter. Remember, that's the units of the forces. This is the resultant force per inch of leg of weld. So next, what we need to do is, once we have the resultant, we need to calculate the leg length. The formula for the leg length, which is H, is just the resultant force divided by the force allowable, right? So if you remember, the weld material used in this example was E60. So we can go to the table and look at what is the allowable force per inch of leg for an E60 material. And we're going to go ahead and use the values for the bridge type structures, which means that this guy can handle 8,800 pounds per inch, and this quantity is always per inch of leg length. Now on the top we have the resultant force in Newton per millimeter, right? And in this formula we have pounds and inches, so we need to convert before we put it in that formula. So we need to convert from newtons to pound force. As well, we need to convert from millimeters to inches. So we know that 1 Newton equals 0.22481 pounds. And we also know that 1 inch is the same thing as 25.4 millimeters. So we go ahead and multiply this through. We get a force of 3,049 pounds per inch. So this is the resultant force, which is 3,049 pounds per inch. Now remember, before we go ahead and calculate this, the problem was asking for a safety factor of 2.5. So we're gonna go ahead and multiply here times 2.5 on the resultant. So this is like a safety factor on the overload. It's another way they call it. Basically, we're gonna take that resultant force and we're gonna multiply it times 2.5. And then it's gonna get divided by 8,800 pounds per inch. Remember, that is the allowable force per inch of leg length. So every inch of leg length on the weld can take this equivalent force. Let's look at what's going to happen to the units. Pounds per inch is going to cancel with pounds per inch. But remember, this quantity is on a per inch basis, right? So this inch on the denominator of the denominator is going to go to the numerator. And so basically, whatever comes out of the calculator is going to have units of inches. Well, if I plug it in the calculator, I get 0.866 inches. However, we were working on this problem and it was all units of newtons and millimeters, right? So if we want to go ahead and report the answer in millimeters, well, we have to convert back to millimeters. Well, we know that 1 inch is 25.4 millimeters. So if we multiply again by 25.4, we get a leg length H of 22 millimeters. So there we go. That means that when we do a weld call out, which some of you will do once you're out in the field, what we need to be able to specify to make sure this weld is okay is that it has a leg length of 22 millimeters. Again, if you remember what that looks like is if we look, for example, at this right hand side, we're gonna have the tube kind of doing something like this. It's gonna be lying on the plate, and so that weld, let me go ahead and do it in green, has to be 22 millimeters high and 22 millimeters here on length. And hopefully when the weld gets deposited, it's done correctly and it's gonna look concave like this. And again, this is 22 as well as this distance is 22. I think this problem is super neat because from the statics, we kept on saying, oh, these assemblies are in, you know, static equilibrium. We have a fixed connection. It's not moving. It's not rotating, right? It's not translating. And back in the day, we just told you, oh, well, imagine it like it's stuck on concrete. But in reality, right, we don't stick everything on concrete. We can weld stuff to make it put together. And that's it. So now you know what the weld size is. To weld this to the plate. On a similar fashion, if you wanted to and wanted to determine what the weld length, right, we can kind of follow the same analysis and figure out, let me do green so you can see it, what the weld size would be at this point, right? That's another neat thing that we can do. We would follow almost the same procedures, except we would be looking at what are the forces now at this plane over here. So hopefully you enjoyed the example. If you have any questions or if you picked up on any mistakes, do let me know in the comments down below. Otherwise, we'll see you on the next one.